Welcome, chemistry students. This video is covering the introductory topic on electrochemistry. We will have redox reaction. And these are the objectives. Number 1, define oxidation and redox reactions. And 2, balance a redox reaction using the change in oxidation number. What is a redox reaction? Redox reaction is any reaction that involves transfer of electrons. So regardless of the type of reaction, be it a combination, decomposition, single replacement, or double replacement, for as long as there is transfer of electrons, the reaction may be considered a redox reaction. What is an oxidation number? This is most important in identifying or determining whether a reaction can be categorized as a redox reaction. An oxidation number is an arbitrary number that may be assigned to an atom to represent the number of electrons lost or gained. We sometimes mistake oxidation number as charge, electric charge, or valence number. Sometimes we can use the idea of valence electrons to determine the oxidation number. We have some rules. Number 1, a metal or a non-metal in the free state is assigned an oxidation number of 0. So whenever you see an element or a substance in a free state in a chemical equation, the oxidation number is always 0. For example, you see zinc in a chemical reaction, free, uncombined, the oxidation number is 0. Hydrogen molecule, whether it has 2 or more atoms in one unit, for as long as it's free, it has no other atom combined with it, the oxidation number is also 0. So same thing with phosphorus here, with that are 4 in one unit, still uncombined, free, the oxidation number is 0. Number 2, a monoatomic ion has an oxidation number equal to its valence number or charge. For example, calcium has a valence number or charge of positive 2, fixed charge of positive 2. So automatically, since this is a monoatomic ion, its charge or valence number positive 2 is the same as its oxidation number. Same with fluorine, negative 1, aluminum, positive 1, and all the other monoatomic ions that we have studied in chemistry 1. So those monoatomic ions, either with the fixed or variable charges, their oxidation number is the same as their valence number or charge. Number 3, in its compounds, hydrogen atom is always assigned an oxidation number of positive 1. If in number 1 rule, it says that any element or any atom of an element in their free state, uncombined, the oxidation number is 0 whenever a hydrogen is combined. In rule number 3, whenever hydrogen is combined with another atom of another element, the oxidation number is always positive 1. Like in water, its oxidation number is positive 1. In ammonia, in acetic acid, so oxidation number of hydrogen in combined state is positive 1. In rule number 4, in its compounds, oxygen atom is assigned an oxidation number of negative 2. So if hydrogen in combined state has an oxidation number of positive 1, oxygen in combined state has an oxidation number of negative 2. So in water, hydrogen is positive 1, oxygen is negative 2. In the compound sulfuric acid, it's also negative 2. In acetic acid, oxygen, since combined, is always negative. Rule number 5, the sum of the oxidation number of all atoms in a polyatomic group is equal to the net charge of the group 0. So we assume here a neutral compound, a neutral substance with the net charge of 0. For example, water, the net charge is 0. That 0 is taken from the sum of the number of atoms multiplied by the oxidation number. We have 2 hydrogen times oxidation number of hydrogen positive 1 plus 1 oxygen times the oxidation number of oxygen negative 2, that's positive 2 plus -2 is equal to 0. In another compound, the oxidation number of sulfur can be determined as follows. So we have three different kinds of atoms here: hydrogen, sulfur, and oxygen. How many hydrogen, how many sulfur, and how many oxygen multiplied by their oxidation number? The net charge must be 0. So we have 2 hydrogen times atomic oxidation number +1, plus we have 1 sulfur times unknown oxidation number, plus 4 hydrogen times oxidation number -2 equals a net charge 0. S then is equal to +6 because 2 times 1 of hydrogen is 2 plus S minus -8. Combining +2 and -8 will have -6. Transposing -6 to the other side of the equation to leave sulfur atom in one side of the equation, we will have -6 turned or converted to +6. This polyatomic ion, where there is net charge of -3, the oxidation number of phosphorus can be determined as follows. So we have 1 phosphorus times unknown oxidation number of phosphorus plus 4 oxygen times oxidation number of oxygen according to rule number 4 is always -2 when combined equals the net charge of not 0 this time. The net charge is -3. We have phosphorus is equal to +5. +5 is taken as we multiply 4 oxygen times -2 oxidation number is -8. Transposing -8 to the right side of the equation, converting it to +8, combining -3 and +8 will have +5. So the oxidation number of phosphorus in phosphate ion with a net charge of -3 is +5. For example, we have this simple equation. 1 mole of solid sulfur reacts with 1 mole of molecular oxygen, forming gaseous sulfur dioxide. So, considering the rules that we have discussed in the previous slides, according to the rules, for example, number 1, an atom of an element, whether metal or a non-metal, whenever free and combined, has an oxidation number of 0. Notice that the two, let me just add a highlighter. Okay. Notice that we have reactants that are free and combined. So automatically, according to rule number 1, their oxidation numbers are 0, as you can see here written on top of the symbols. Oxygen in the product side is already combined. So according to rule number 4, oxygen when combined has an oxidation number of -2. So we have an unknown sulfur as oxidation number following the fifth rule. The net charge 0. Given the net charge 0 for the compound sulfur dioxide will mean +4 oxidation number for sulfur. So that is 1 times +4 is equal to +4. 2 atoms of oxygen times -2 will have -4. Combining +4 and -2 will have a net charge for this compound, neutral compound, 0. Which between our two atoms in the left side of the equation, reactant side, did increase in oxidation number. Notice that sulfur initial oxidation number, that is in the left side, reactant side, we have 0. After the reaction in the right side, it becomes +4. Oxidation is true for an atom that did increase in oxidation number. So if between sulfur and oxygen in this reaction increased in oxidation number after the reaction, then sulfur is the one that undergoes oxidation or is oxidized in the reaction. The atom where it is present, that substance where the atom, oxidized atom is combined or is present, means that that substance is the reducing agent. Meaning, that substance carries the oxidized atom and causes the other to be reduced. That's why it's called reducing agent. Reduction is underwent by an atom that decreased in oxidation number. Since we only have two atoms here, oxygen is the one that decreased in oxidation number. From in the left, we have 0. After the reaction, it went down to -2. So that means there is a decrease in oxidation number. Hence, oxygen is reduced or undergoes reduction. That substance where it is present or carrying the reduced atom serves or acts as an oxidizing agent. It causes the other substance to be oxidized. That's why it's called oxidizing agent. So every time there's increase and decrease in oxidation number between two atoms of elements in a reaction, there is definitely loss and gain of electrons because there is increase and decrease of oxidation number. So that reaction is considered a redox reaction. Let's have this simple reaction for an example. To interpret, we have 1 mole of liquid ferric oxide react with 3 moles of carbon monoxide gas to produce 2 moles of solid iron and 3 moles of carbon dioxide gas. So the coefficients 3, 2, and 3 are added coefficients to balance the equation. So to balance a redox reaction is to balance first the number of atoms of all the elements in both sides of the equation. Then assign all the oxidation numbers for the individual atoms in the reaction. So as you can see here, from the left side to the right, we have the oxidation numbers of the individual atoms. Iron is, let me use a pointer. Okay. So for the oxidation numbers of the individual atoms, we have iron is +3. Because oxygen is combined here, rule number 4 says that oxygen when combined is having an oxidation number of -2. So if it's -2 times 3 oxygen atoms in this compound equals -6. Iron has subscript 2, so what number can you multiply by 2 so that when you add to -6 you will get a net charge of 0? That will be +3. So even if you don't use algebraic expression, you can mentally determine the oxidation number given the automatic assignment of the oxidation numbers as emphasized in the set of rules for assigning oxidation numbers. And then for the other reactant, oxygen also is combined here, so its oxidation number is -2. We have ratio of carbon is to oxygen 1. So what number can you multiply by -2? So when you add, what number can you add? Can you multiply by carbon 1 so that when you add to the oxidation number -2 of oxygen, you will get a summation of a net charge of 0. So that is +2. That's why carbon is +2 because oxygen is automatically -2. In the product side, we have iron becoming uncombined here, free. Therefore, according to rule number 1, oxidation number is 0. In the other product, we have carbon dioxide. Oxygen is again combined, -2, but multiplying by 2 atoms of oxygen in the compound, we have -4. Carbon 1 times +4 is +4. +4 plus -4 is equal to the net charge 0. So looking at the oxidation numbers, as we mentioned in the previous slides, whichever atom did undergo an increase in oxidation number is the one that is oxidized in the reaction. On the other hand, that atom that did decrease in oxidation number is the one that undergoes the reduction in the reaction. So to easily identify the oxidation, the reducing agent, reduction, and oxidizing agent. So which atom did undergo oxidation, or which did undergo reduction, and which acts as oxidizing agent and acting as reducing agent, we can use the acronym GEROA. GEROA, which means gain of electrons, means that atom undergoes reduction. That substance that carries the reduced atom is the oxidizing agent. So between iron and oxygen here, or between carbon and oxygen, or among iron, oxygen, and carbon, among the three, notice that iron decreased in oxidation number. Initially, in the left side of the equation, you see its oxidation number as +3. After the reaction, it went down to 0. Since there is decrease in oxidation number, iron is the atom that did undergo reduction. The substance, the reactant that carries that atom that did undergo reduction is what we consider the oxidizing agent, meaning it caused the other substance to be oxidized. Hence, is called an oxidizing agent. For the other substance that did increase in oxidation number, that means that atom did lose electrons and is oxidized. And the substance that carries that atom that is oxidized is considered the reducing agent because it caused the other to be reduced. So among the three, because we have identified that iron is the one that is reduced, so which between oxygen and carbon did increase in oxidation number and is therefore labeled or considered identified as the oxidized substance or atom. So between oxygen and carbon, notice that carbon is the one that increased in oxidation number. Oxygen remained to be -2 even after the reaction. Carbon initially is +2. After the reaction, it went up to +4. Since there is increase in oxidation number, carbon is what we consider the atom that is oxidized. That substance that carries carbon is considered the reducing agent. This means that that substance, carbon monoxide, being the reducing agent, caused the other substance, iron 3 oxide, to be reduced. That's why it's called reducing agent. So you just remember the acronyms GEROA, which means gain of electrons results to reduction. That substance that carries the reduced atom is the oxidizing agent. LEORA means loss of electron results to oxidation. That substance that carries the atom that is oxidized is the reducing agent. Now, how do we balance the number of electrons lost and gained? So as I said, the first thing to do is to balance chemically the reaction. That's why we need to add the necessary coefficients to make sure that the number of atoms of each element in both sides of the equation are the same. Because balancing the number of electrons lost and gained needs the number of the equal number of each atom of atoms of each element in both sides of the equation. So to determine the number of atoms lost or gained, we can use the formula open and close parentheses change in oxidation number, that is final oxidation number minus initial oxidation number multiplied by the number of atoms of that substance or element. So for the number of electrons gained, again, which among the three atoms did gain electrons? It is iron. Iron is the one that is reduced, that gained electrons. The question is, how many electrons did it gain after the reaction? So to get the number of electrons it gained, we have to use the formula final oxidation number minus initial multiplied by the number of atoms on both sides since it is equal. So either side you can get the that same number of atoms. So iron's final oxidation number is 0. So the final oxidation number can be taken in the right side, from the right side of the equation. So that is 0 minus its initial in the left side is positive 3. After getting the difference, 0 minus positive 3, change the sign of positive 3 to negative 3. 0 plus, and then proceeding to addition, 0 plus negative 3 will give you negative 3. Negative 3, difference here, multiplied by how many iron atoms in both sides of the equation? We have 2. So negative 3 times 2 equals negative 6. Negative here means gain of electrons. So that means that there are 6 electrons gained by iron in the redox reaction. For the number of electrons lost, so we have identified that carbon is the one that did undergo oxidation. So we calculate the number of electrons lost by using the same formula, final oxidation number of carbon. So in the right side, we have positive 4 minus the initial positive 2. Changing the sign of negative 2 here, we have, positive to negative 2, we'll have positive 4, proceeding to addition, plus negative 2, we'll have positive 2. Positive 2 times the total number of carbon on both sides of the equation, we have 3. So 2 times positive 3, or 3, is equal to positive 6. Therefore, 6 electrons were lost by carbon. Make sure that you have to remember that the number of electrons must always be equal to the number of electrons gained. The transfer of electrons, the number of electrons transferred must be complete. So one atom loses that number of electrons and the other atom gains the same number of electrons. So that's how you balance a redox reaction using the change in oxidation number method. So using the change in oxidation number method, you may practice to balance this equation. You just refer to the example I gave. So that will be all for this simple introduction to electrochemistry.